Capacitor. It consists of two conductors insulating from one another with nothing in between them. So here in diagram we see two conductors, conductor 1 and conductor 2. Conductor 1 is at potential phi 1 and conductor 2 is at potential phi 2. So in this case capacitance of this system will be given by C is equal to Q upon phi 1 2, where phi 1 2 is equal to phi 1 minus phi 2, which is potential difference between two conductors, and Q is the charge stored on one plate of the conductor. And in case of parallel plate capacitor, C is given by epsilon naught A by S, where A is the area of the plate of capacitor and S is the distance between them. This can be shown in this way diagrammatically. These types of capacitor in which there is nothing in between the plates of capacitor is called vacuum capacitors. Called vacuum capacitors. These types of capacitors are used chiefly where high and rapidly varying potentials are involved. But most capacitors we use are one in which between the plates there is some sort of non-conducting liquid or solid substance is there. For example, this substance can be polyethylene, plastic, paraffin wax, silicon, and there are some other examples also. In such cases, now capacitance won't be equal to epsilon naught A upon distance between the plates. In such cases, we find that more charge will be stored on the plates. That is, since Q increases, it implies C also increases because C is given by Q upon phi 1 2. So in such cases capacitance is greater than epsilon naught A upon distance between the plates of capacitor. So now we are going to understand why this is happening. So for this consider a capacitor and we insert a plastic slab between the plates. Since plastic consists of molecules and molecules have positive and negative charges in them, and so if we see in this diagram it will be more clear here. So here a plate A and a plate B. Positive charge is on plate A and negative charge is on plate B. So due to this electric field be set up here, and this is our plastic slab. I will show two molecules here, positive, negative, and negative, positive. Let's go on for another one, positive, negative. So what's going to happen is, as electric field is set up, the positive charges are going to move in the downward direction. Positive charge is going to move in downward direction and negative are going to move in upward direction. The electric field that is electric field will be pulling up the negative charges and pulling down to the positive charges. Note that there is an important point to note that is, nothing is moving very far. Okay, so there will be only some displacement of the charges, some displacement of charges, So what happens is, the overall effect is that the negative charge distribution and positive charge distribution are slightly displaced to one another now. That is, now these some positive charges and negative charges, they will interact, then the whole potential will be reduced. But we have also a battery applied here. Battery is at potential V. Now the task of the battery is to maintain a potential difference between A and plate B of V. Now to maintain that potential difference, battery will give some positive charges, positive and negative charges will be there to maintain a constant potential difference of V volt. This can be put as in the presence of a induced layer of negative charge below the upper plate, the Q on the plate will increase as we have shown here. So now the ratio between the Q new, which is new charge that is stored on the plate of capacitor, versus QO, which is Q old, the ratio is called kappa. Kappa. This kappa is known as dielectric constant, and we also have a relation between the old and new capacitance, which is this, a dielectric constant. If you have any doubt, please let me know in the comments.